Look up at the night sky on a clear evening and you might see a faint band of light stretching across the darkness, our Milky Way galaxy. But here's what will absolutely shatter your perspective. If our entire galaxy were shrunk down to the size of a dinner plate, the observable universe would stretch beyond the orbit of Pluto. Today we're embarking on a mind-bending journey through cosmic scales so vast that they challenge the very limits of human comprehension. Now let's begin this incredible journey. The Milky Way galaxy is our cosmic home, a vast spiral of stars, gas and dust that spans roughly 100,000 light-years from edge to edge. To put this in perspective, light, which can circle Earth 7.5 times in just 1 second, takes 100,000 years to travel from one side of our galaxy to the other. If you could somehow travel at the speed of light, you'd spend your entire lifetime just getting halfway across our galactic neighborhood. Our galaxy contains between 200 billion and 400 billion stars, each one a sun in its own right, many hosting planetary systems that could harbor life. The sheer number is staggering. If you counted one star every second without stopping, it would take you over 12,000 years just to count the lower estimate. And that's assuming you never sleep, never eat, never take a break. But here's where the scale becomes truly mind-boggling. The Milky Way, despite its incredible size, is just one galaxy among an estimated 2 trillion galaxies in the observable universe. That's 2 followed by 12 zeros. A number so large that if each galaxy were a grain of sand, you'd have enough sand to cover the entire United States to a depth of several feet. The European Space Agency's Gaia mission has revolutionized our understanding of our galactic home by mapping over 1 billion stars with unprecedented precision. Launched in 2013, this remarkable spacecraft has created the most detailed three-dimensional map of our galaxy ever produced, revealing that the Milky Way is far more complex and dynamic than we ever imagined. Gaia's observations have shown that our galaxy isn't a static structure but a living, breathing entity constantly in motion. Stars orbit the galactic center in vast, sweeping paths that take hundreds of millions of years to complete. Our own Sun has made roughly 20 trips around the galaxy since it formed 4.5 billion years ago, each journey taking about 225 million years. The center of our galaxy harbors a supermassive black hole called Sagittarius A star, weighing roughly 4 million times as much as our Sun. This cosmic monster sits 26,000 light-years away from us, influencing the orbits of stars throughout the galaxy. The Event Horizon Telescope captured the first image of this black hole in 2022, revealing the shadow of the event horizon against the glowing accretion disk of superheated gas. Our solar system occupies a rather unremarkable position in the galaxy, located about halfway between the center and the edge in what astronomers call the Orion arm, a minor spiral arm that's really more of a spur connecting two major arms. We're cosmic suburbanites, living neither in the bustling downtown of the galactic center nor in the sparse countryside of the outer rim. This location turns out to be quite fortunate for life. The galactic center is a violent place, filled with intense radiation, frequent supernova explosions and gravitational chaos that would make stable planetary systems difficult to maintain. The outer regions, while peaceful, lack the heavy elements necessary for rocky planet formation and complex chemistry. The concept of the galactic habitable zone suggests that there's a sweet spot in galaxies where conditions are just right for life to emerge and thrive. We happen to live in this cosmic Goldilocks zone where stellar densities are moderate, heavy element abundances are sufficient, and catastrophic events are rare enough to allow billions of years of stable evolution. If you're finding these cosmic scales as mind-blowing as I am, I'd really appreciate it if you could hit that subscribe button and give this video a thumbs up. We're just getting started on this journey through the universe's most incredible scales, and your support helps me continue bringing these amazing discoveries to light. But our galaxy, vast as it is, exists within an even larger structure called the local group. This gravitationally bound collection of galaxies spans roughly 10 million light-years and contains over 80 galaxies, though most are small dwarf galaxies with just millions or billions of stars compared to our galaxy's hundreds of billions. The local group is dominated by three large spiral galaxies: our Milky Way, the Andromeda galaxy, and the smaller Triangulum galaxy. Andromeda, located 2.5 million light-years away, is the most distant object visible to the naked eye. When you look at Andromeda in the night sky, you're seeing light that left that galaxy when our earliest human ancestors were just beginning to use stone tools. Andromeda is approaching us at roughly 110 kilometers per second, and in about 4.5 billion years it will collide with the Milky Way in a cosmic dance that will reshape both galaxies. Computer simulations show that despite the violence of this collision on galactic scales, individual star systems will likely remain intact due to the vast distances between stars. The Hubble Space Telescope has provided stunning images of galaxy collisions throughout the universe, showing us previews of our own galactic future. These cosmic crashes, while destructive to the original galactic structures, often trigger intense bursts of star formation and can create beautiful new galactic shapes and configurations. Beyond the local group lies an even grander structure, the Virgo Supercluster, a massive collection of galaxy groups and clusters that spans roughly 110 million light-years. Our local group is just a tiny component of this vast cosmic web, slowly falling toward the Virgo cluster under the influence of its immense gravitational pull. The Virgo cluster itself contains over 1,300 galaxies, including massive elliptical galaxies that dwarf our Milky Way. These galactic giants can contain trillions of stars and span hundreds of thousands of light-years. M87, one of the largest galaxies in the Virgo cluster, is home to the first black hole ever directly imaged by the Event Horizon Telescope. But even the Virgo supercluster is dwarfed by larger structures in the universe. The Laniakea supercluster, identified in 2014 through detailed mapping of galaxy motions, contains roughly 100,000 galaxies spread across 520 million light-years. Our entire local group is just a tiny speck within this vast cosmic structure. The discovery of Laniakea was made possible by mapping the peculiar velocities of galaxies, their motions relative to the overall expansion of the universe. These motions reveal the underlying gravitational structure of the cosmos, showing how matter is organized on the largest scales and how galaxies flow along cosmic highways of dark matter. Dark matter, that mysterious substance that makes up roughly 85% of all matter in the universe, provides the gravitational scaffolding for all cosmic structures. Without dark matter, galaxies couldn't form, galaxy clusters couldn't hold together, and the large-scale structure of the universe would look completely different. The cosmic web, revealed through computer simulations and observational surveys, shows how matter is distributed throughout the universe on the largest scales. Galaxies and galaxy clusters lie along filaments of dark matter that stretch across hundreds of millions of light-years, separated by vast cosmic voids that contain very little matter. These cosmic voids represent some of the most empty regions in the universe, containing less than 1/10 the average density of matter. The Bootes void, also known as the Great Nothing, spans roughly 330 million light-years and contains almost no galaxies. If Earth were located in the center of this void, we wouldn't have discovered other galaxies until the 1960s, fundamentally altering our understanding of the universe's scale and structure. The largest known structure in the observable universe is the Hercules Corona Borealis Great Wall, a massive collection of galaxy clusters that stretches over 10 billion light-years across. This structure is so large that light takes over 10 billion years to travel from one end to the other, a significant fraction of the age of the universe itself. These enormous structures challenge our understanding of how the universe evolved from the nearly uniform conditions observed in the cosmic microwave background to the complex web of galaxies we see today. The slight density fluctuations present just 380,000 years after the Big Bang somehow grew into the massive structures we observe across billions of light-years. The Planck satellite, which mapped the cosmic microwave background with unprecedented precision, revealed these primordial fluctuations in exquisite detail. These tiny variations in temperature, just a few millionths of a degree, represent the seeds from which all cosmic structure grew through the relentless pull of gravity over billions of years. Computer simulations like the Millennium Simulation and the Illustris project have modeled the growth of cosmic structure from these early seeds to the present day. These simulations require some of the world's most powerful supercomputers and can track the evolution of billions of dark matter particles over cosmic time, revealing how the universe's web-like structure emerged. The results of these simulations match observations remarkably well, confirming our understanding of how gravity shapes the universe on the largest scales. They show how dark matter halos form first, then attract ordinary matter that eventually condenses into stars and galaxies within these gravitational wells. But here's where the scale becomes truly humbling. Everything we've discussed so far, our galaxy, the local group, the Virgo supercluster, even the largest known structures, exists within just the observable universe. This represents only the portion of the cosmos from which light has had time to reach us since the Big Bang roughly 13.8 billion years ago. The observable universe has a radius of about 46.5 billion light-years, not 13.8 billion light-years as you might expect. This difference arises because space itself has been expanding during the time light has been traveling toward us. The galaxies we see at the edge of the observable universe are now much farther away than they were when their light began its journey to Earth. Speaking of the challenges of cosmic travel, the vast scales we're discussing make interstellar and intergalactic travel almost impossibly difficult. If you're curious about why we might never be able to leave our galaxy despite all our technological advances, you should check out my video, "This is Why We Can't Leave the Milky Way." It explores the mind-bending physics and engineering challenges that make even traveling to nearby stars seem like an insurmountable obstacle, let alone venturing beyond our galactic boundaries. The link is in the description and pinned on the comments. Beyond the observable universe lies the entire universe, which could be infinite in extent. If the universe is indeed infinite, then everything that can happen will happen somewhere, including exact copies of you reading this script in galaxies far beyond our cosmic horizon. This mind-bending possibility emerges naturally from our current understanding of cosmic inflation and the fundamental nature of space and time. The cosmic microwave background represents the most distant thing we can observe with electromagnetic radiation. This faint glow, discovered accidentally by Arno Penzias and Robert Wilson in 1964, is the afterglow of the Big Bang itself, stretched and cooled by billions of years of cosmic expansion. When we observe the cosmic microwave background, we're seeing the universe as it was just 380,000 years after the Big Bang, when it first became transparent to light. Before this epoch of recombination, the universe was filled with a hot, dense plasma that scattered photons and prevented light from traveling freely through space. The temperature of the cosmic microwave background is just 2.7 Kelvin above absolute zero, but it was once as hot as the surface of the Sun. This dramatic cooling is a direct result of cosmic expansion, which stretches the wavelengths of photons and reduces their energy as the universe grows larger and larger. The nearly perfect uniformity of the cosmic microwave background across the entire sky presents one of cosmology's greatest puzzles. Regions of the sky separated by more than 2 degrees show the same temperature to within 1 part in 100,000. Yet these regions were never in causal contact according to standard Big Bang theory. This horizon problem led to the development of cosmic inflation theory, which proposes that the universe underwent a period of exponential expansion in its first fraction of a second. During inflation, regions that were initially in causal contact were stretched apart faster than light could travel between them, explaining the observed uniformity. Inflation also explains why the universe appears to be geometrically flat on large scales. Just as the surface of a balloon appears flat to an ant walking on it, cosmic inflation stretched space so much that any initial curvature was flattened out, leaving us with the flat universe we observe today. The inflationary epoch lasted from roughly 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang. During this incredibly brief period, the universe expanded by a factor of at least 10 to the 26, transforming a region smaller than a proton into something larger than a grapefruit. This exponential expansion was driven by a hypothetical quantum field called the inflaton, which had the unusual property of creating repulsive gravity. When the inflaton field finally decayed, it released enormous amounts of energy that heated the universe and created the hot, dense conditions of the traditional Big Bang model. The quantum fluctuations in the inflaton field during inflation were stretched to cosmic scales and became the seeds for all structure formation in the universe. These tiny quantum variations, amplified by inflation, eventually grew into the galaxies, galaxy clusters, and cosmic web we observe today. Different models of inflation make different predictions about the nature of these primordial fluctuations and their observable consequences. The Planck satellite's precise measurements of the cosmic microwave background have ruled out many inflationary models while supporting others, helping to refine our understanding of the universe's earliest moments. The concept of eternal inflation suggests that inflation never completely ends, but continues in some regions of space while ending in others. This process would create an infinite number of bubble universes, each with potentially different physical laws and constants. Our observable universe would be just one bubble in this vast multiverse. If eternal inflation is correct, then the universe is not only larger than we can observe, but contains regions with fundamentally different physics. Some bubbles might have different numbers of spatial dimensions, different particle physics, or even different values for the speed of light and other fundamental constants. The multiverse hypothesis, while scientifically motivated, raises profound philosophical questions about the nature of reality and our place within it. If every possible universe exists somewhere in the multiverse, what makes our particular universe special? How can we test theories about regions of space that are forever beyond our observation? These questions push the boundaries of science and philosophy, challenging us to think carefully about what we can know and how we can know it. The scientific method relies on observation and experimentation, but the multiverse hypothesis deals with regions that are fundamentally unobservable from our cosmic bubble. Despite these challenges, the multiverse concept has gained support from several independent lines of theoretical development, including string theory, quantum mechanics, and cosmology. While we may never be able to directly observe other universes, the mathematical consistency and explanatory power of multiverse theories continue to attract scientific interest. The anthropic principle offers one approach to understanding our place in a potential multiverse. This principle suggests that we observe the universe to have properties compatible with our existence precisely because we exist to observe it. In a multiverse with varying physical laws, only universes capable of supporting observers would be observed. The anthropic principle helps explain some of the apparent fine-tuning we observe in our universe's physical constants. The strength of the electromagnetic force, the mass of the electron, and dozens of other parameters seem precisely calibrated to allow the formation of atoms, stars, and ultimately life. In a multiverse, this fine-tuning might simply reflect the fact that we can only exist in universes where these parameters fall within life-permitting ranges. However, the anthropic principle remains controversial among scientists. Critics argue that it abandons the search for deeper physical explanations in favor of selection effects. They contend that apparent fine-tuning might have fundamental explanations we haven't yet discovered, rather than being the result of a cosmic lottery in a multiverse. The debate over fine-tuning and the anthropic principle illustrates how our understanding of cosmic scale extends beyond mere size to encompass the fundamental nature of physical reality itself. The universe's vastness in space and time is matched by an equally profound depth in the laws and constants that govern its behavior. Recent observations have revealed that our understanding of cosmic scale continues to evolve. The James Webb Space Telescope, launched in 2021, has observed galaxies that formed when the universe was less than 400 million years old. These ancient galaxies appear surprisingly massive and mature, challenging our models of early cosmic evolution. The discovery of these early massive galaxies suggests that structure formation in the young universe proceeded more rapidly than previously thought. This finding has implications for our understanding of dark matter, star formation, and the growth of supermassive black holes in the universe's first billion years. Webb's infrared vision allows it to peer through cosmic dust and observe the most distant galaxies ever detected. Some of these galaxies have redshifts exceeding 13, meaning we're seeing them as they were less than 400 million years after the Big Bang. The light from these galaxies has been traveling toward us for over 13 billion years. The concept of redshift provides a crucial tool for measuring cosmic distances and understanding the universe's expansion. As space expands, it stretches the wavelengths of light traveling through it, shifting visible light toward longer, redder wavelengths. The amount of redshift tells us both how far away an object is and how fast space was expanding when its light was emitted. The Hubble Space Telescope's observations of distant supernovae in the 1990s revealed that the universe's expansion is accelerating, driven by a mysterious component called dark energy. This discovery earned the 2011 Nobel Prize in Physics and fundamentally changed our understanding of cosmic evolution. Dark energy makes up roughly 68% of the universe's total energy density, yet we have no idea what it actually is. It behaves like a form of energy that fills all of space and exerts a repulsive gravitational effect, causing the expansion of space to accelerate over time. The acceleration of cosmic expansion has profound implications for the universe's future and the ultimate fate of all cosmic structures. As expansion accelerates, galaxies outside our local group will eventually recede so fast that their light can never reach us, effectively disappearing beyond our cosmic horizon. In the far future, perhaps 100 billion years from now, observers in our galaxy will see a much emptier universe. The cosmic microwave background will have cooled and redshifted beyond detection, and evidence for the Big Bang and cosmic expansion will have literally disappeared beyond the observable horizon. This cosmic loneliness represents one of the most profound consequences of our universe's accelerating expansion. Future civilizations will inherit a universe that appears static and eternal, with no evidence of its dynamic history or the vast cosmic web that once connected galaxies across billions of light years. The study of cosmic scale has also revealed the crucial role of dark matter in shaping the universe's structure. This invisible component, which outweighs ordinary matter by a factor of 5 to 1, provides the gravitational scaffolding for all cosmic structures, from galaxies to superclusters. Computer simulations of structure formation show that without dark matter, the universe would look completely different. Ordinary matter alone couldn't have formed the complex web of galaxies we observe today. The gravitational pull of dark matter was essential for gathering ordinary matter into the dense clumps that became stars and galaxies. The nature of dark matter remains one of the greatest mysteries in modern physics. Despite decades of searching, we've never directly detected a dark matter particle, though we can observe its gravitational effects on visible matter throughout the universe. Underground detectors, particle accelerators, and space-based telescopes continue the hunt for this elusive component. Leading candidates for dark matter include weakly interacting massive particles, axions, and sterile neutrinos. Each possibility would have different implications for particle physics and our understanding of the fundamental forces that govern the universe. The Large Hadron Collider at CERN has searched for dark matter particles by recreating the high-energy conditions that existed shortly after the Big Bang. While these experiments haven't yet detected dark matter directly, they've placed important constraints on its properties and interactions with ordinary matter. Space-based observatories like the Euclid mission and the Nancy Grace Roman Space Telescope will map the distribution of dark matter throughout the universe by observing how its gravity bends and distorts the light from distant galaxies. This technique, called weak gravitational lensing, provides a way to map invisible dark matter using its effects on visible light. The cosmic web of dark matter filaments that connects galaxies across the universe represents structure on scales that dwarf even the largest galaxy clusters. These filaments, predicted by computer simulations and confirmed by observations, channel gas and galaxies along cosmic highways that span hundreds of millions of light-years. The intersection points where multiple dark matter filaments meet become the sites of massive galaxy clusters, the largest gravitationally bound structures in the universe. These clusters can contain thousands of galaxies and have total masses exceeding 1 quadrillion times the mass of our Sun. The Coma cluster, located roughly 320 million light-years away, contains over 1,000 known galaxies and serves as a prototype for understanding cluster physics. The hot gas between galaxies in the cluster glows brightly in X-rays, revealing temperatures of tens of millions of degrees heated by the cluster's immense gravitational field. Galaxy clusters serve as cosmic laboratories for studying dark matter, dark energy, and the physics of matter under extreme conditions. The collision between galaxy clusters creates some of the most energetic events in the universe since the Big Bang, accelerating particles to enormous energies and generating shock waves that span millions of light-years. The Bullet cluster, formed by the collision of two galaxy clusters, provides some of the strongest evidence for dark matter's existence. Observations show that the visible matter and dark matter have separated during the collision, with dark matter passing through largely unaffected, while the hot gas between galaxies was slowed by electromagnetic interactions. These cluster collisions also provide insights into the nature of dark matter itself. The fact that dark matter clumps pass through each other with minimal interaction places constraints on dark matter's properties and helps rule out certain theoretical models. The study of galaxy cluster evolution over cosmic time reveals how the largest structures in the universe have grown through mergers and accretion. The most massive clusters we observe today are still assembling, having grown from much smaller structures in the early universe through billions of years of gravitational attraction. The abundance of galaxy clusters at different cosmic epochs provides a sensitive test of cosmological models and the properties of dark energy. As dark energy accelerates cosmic expansion, it becomes increasingly difficult for matter to collapse into new clusters, affecting the rate of cluster formation over time. Precision measurements of cluster abundances by surveys like the Dark Energy Survey and the upcoming Vera Rubin Observatory will provide new constraints on dark energy's properties and its evolution over cosmic history. These observations could reveal whether dark energy is truly constant or changes over time. The Vera Rubin Observatory, currently under construction in Chile, will revolutionize our understanding of cosmic scale through its legacy survey of space and time. This ambitious project will photograph the entire visible sky every few nights for 10 years, creating an unprecedented movie of the changing universe and cataloging billions of galaxies across cosmic time. The survey will detect supernovae, track asteroid movements, and map the distribution of dark matter through gravitational lensing effects. By observing how cosmic structures evolve over the survey's decade-long duration, astronomers will gain new insights into the fundamental forces shaping the universe on the largest scales. One of the most profound discoveries about cosmic scale came from studying Type Ia supernovae, stellar explosions that serve as standard candles for measuring cosmic distances. These explosions have remarkably consistent peak brightness, allowing astronomers to determine how far away they are by comparing their apparent brightness to their known intrinsic luminosity. The Supernova Cosmology Project and the High-Z Supernova Search Team used these stellar explosions to map the expansion history of the universe. Their shocking discovery that distant supernovae appeared dimmer than expected revealed that cosmic expansion is accelerating, fundamentally changing our understanding of the universe's fate. This acceleration implies that some form of energy with repulsive gravitational effects, dubbed dark energy, dominates the universe's energy budget. The discovery earned Saul Perlmutter, Brian Schmidt, and Adam Riess the 2011 Nobel Prize in Physics and opened an entirely new chapter in cosmology. The nature of dark energy remains one of the deepest mysteries in science. It could be Einstein's cosmological constant, a property of space itself that creates a constant energy density throughout the universe. Alternatively, it might be a dynamic field that changes over time, potentially leading to different cosmic fates than a constant would predict. Future observations will test whether dark energy is truly constant or evolves over cosmic time. The Nancy Grace Roman Space Telescope will observe thousands of supernovae across a wide range of cosmic epochs, providing unprecedented precision in measuring dark energy's properties and evolution. The concept of cosmic horizons adds another layer to our understanding of scale in the universe. The particle horizon represents the maximum distance from which light could have reached us since the Big Bang, defining the boundary of the observable universe. Beyond this horizon lie regions of space that remain forever hidden from our view. But there's also an event horizon in our accelerating universe, a boundary beyond which galaxies are receding so fast that any light they emit now will never reach us. This cosmic event horizon is currently located at a distance of roughly 16 billion light-years, and it's slowly shrinking as cosmic acceleration continues. The existence of these horizons means that our observable universe represents just a tiny fraction of the total cosmos. If the universe is infinite, as many cosmological models suggest, then the vast majority of reality lies forever beyond our ability to observe or influence. This cosmic isolation has profound implications for the future of astronomy and our understanding of the universe. In the far future, as cosmic acceleration continues, the observable universe will contain fewer and fewer galaxies, eventually leaving our local group alone in an apparently empty cosmos. The study of gravitational waves has opened an entirely new window on cosmic scale, allowing us to observe the universe through ripples in space-time itself rather than electromagnetic radiation. The Laser Interferometer Gravitational Wave Observatory, or LIGO, first detected these waves in 2015, confirming Einstein's century-old prediction. Gravitational waves travel at the speed of light but can penetrate regions of the universe that are opaque to electromagnetic radiation. They provide a new way to study cosmic phenomena like black hole mergers, neutron-star collisions, and potentially even the Big Bang itself. The merger of two black holes detected by LIGO released more energy in gravitational waves than all the stars in the observable universe emit in light. This incredible energy output, concentrated into a fraction of a second, demonstrates the violent processes that shape cosmic evolution on the largest scales. Future gravitational wave observatories like the Laser Interferometer Space Antenna, or LISA, will detect waves from supermassive black hole mergers throughout the universe. These observations will provide new insights into how the largest black holes formed and evolved over cosmic time. The cosmic microwave background polarization provides another tool for probing the universe's largest scales and earliest moments. The slight polarization patterns in this ancient light carry information about gravitational waves from the inflationary epoch, potentially providing direct evidence for cosmic inflation. The Bicep and Planck experiments have searched for these primordial gravitational wave signatures, placing tight constraints on inflationary models. Future experiments with even greater sensitivity may finally detect the gravitational wave background from inflation, opening a window into physics at energy scales far beyond what we can achieve in particle accelerators. The study of cosmic voids, the vast empty regions between galaxy filaments, has revealed another aspect of cosmic scale that challenges our understanding. These voids can span hundreds of millions of light-years and contain very few galaxies, representing some of the most empty regions in the universe. The Bootes void, discovered in 1981, spans roughly 330 million light-years and contains almost no galaxies. If Earth were located in the center of this void, we wouldn't have discovered other galaxies until much later in human history, fundamentally altering our understanding of the universe's scale and structure. These cosmic voids aren't completely empty, but contain a sparse network of dark matter and gas. The study of void properties provides insights into dark energy's effects on cosmic structure formation and the overall geometry of the universe. Void galaxies, the rare galaxies that do exist within these empty regions, have unusual properties that reflect their isolated environments. They tend to be smaller, bluer, and more actively forming stars than galaxies in denser regions, providing natural laboratories for studying galaxy evolution in extreme environments. The cosmic web's filamentary structure, revealed through large galaxy surveys like the Sloan Digital Sky Survey, shows how matter is organized on the largest scales. These surveys have mapped millions of galaxies across billions of light-years, revealing the intricate network of filaments and voids that characterizes cosmic structure. The 2-degree field galaxy redshift survey and its successors have created 3-dimensional maps of the universe that reveal structures spanning over 1 billion light-years. These maps show that the universe has a sponge-like structure, with galaxies concentrated along filaments surrounding vast empty voids. The baryon acoustic oscillations, regular patterns in galaxy clustering, provide a standard ruler for measuring cosmic distances and the expansion history of the universe. These patterns, imprinted in the cosmic microwave background and preserved in galaxy distributions, offer an independent way to study dark energy and cosmic geometry. The Dark Energy Spectroscopic Instrument, currently conducting a 5-year survey, will measure the distances to 35 million galaxies across 11 billion years of cosmic history. This unprecedented dataset will provide the most precise measurements yet of how cosmic expansion has evolved over time. The concept of cosmic time adds another dimension to our understanding of scale. When we observe distant galaxies, we see them as they were billions of years ago due to light's finite speed. The most distant galaxies observed by the James Webb Space Telescope appear as they were when the universe was less than 400 million years old. This look-back time effect means that astronomy is inherently a historical science. We can never observe the current state of distant objects, only their ancient light that has been traveling toward us for billions of years. The universe we observe is a patchwork of different cosmic epochs, from nearby galaxies we see as they were millions of years ago to the cosmic microwave background from when the universe was just 380,000 years old. The age of the universe itself, 13.8 billion years, provides the ultimate scale for cosmic time. This age has been determined through multiple independent methods, including observations of the cosmic microwave background, measurements of the Hubble constant, and studies of the oldest stars in globular clusters. The remarkable agreement between these different age measurements gives us confidence in our understanding of cosmic chronology. However, recent tensions between different methods of measuring the Hubble constant have raised questions about whether our cosmological model is complete or if new physics might be required. The Hubble tension, as this discrepancy is known, represents one of the most significant challenges in modern cosmology. Measurements of the cosmic microwave background by the Planck satellite suggest the universe is expanding at 67 kilometers per second per megaparsec, while observations of nearby supernovae and Cepheid variable stars indicate a rate of about 73 kilometers per second per megaparsec. This 6% difference might seem small, but it's statistically significant and could indicate new physics beyond our current understanding. Possible explanations include unknown properties of dark energy, additional types of neutrinos, or modifications to our understanding of gravity on cosmic scales. The resolution of the Hubble tension will likely require new observations and potentially new theoretical frameworks. The James Webb Space Telescope's unprecedented infrared capabilities may help resolve this mystery by providing more precise distance measurements to nearby galaxies and better observations of the early universe. The concept of cosmic inflation provides our best current explanation for the universe's large-scale uniformity and structure. During the inflationary epoch, quantum fluctuations were stretched to cosmic scales, creating the density variations that eventually grew into galaxies and galaxy clusters through gravitational attraction. Different inflationary models make different predictions about the statistical properties of these primordial fluctuations. The Planck satellite's precise measurements of the cosmic microwave background have confirmed many predictions of simple inflationary models while ruling out more exotic alternatives. The search for primordial gravitational waves from inflation continues to push the boundaries of observational cosmology. These waves would create distinctive polarization patterns in the cosmic microwave background, providing direct evidence for the inflationary epoch and insights into physics at energy scales approaching the Planck scale. The Planck scale represents the ultimate frontier of physics, where quantum effects and gravity become equally important. At distances of 10 to the negative 35 meters and energies of 10 to the 19th billion electron volts, our current theories of physics break down, and new, unknown physics must take over. Understanding physics at the Planck scale is crucial for developing a complete theory of quantum gravity and understanding the universe's earliest moments. String theory, loop quantum gravity, and other approaches attempt to describe physics in this regime, but experimental tests remain far beyond our current capabilities. The holographic principle, emerging from black hole physics and string theory, suggests that all the information contained in a volume of space can be encoded on its boundary. If true, this principle would fundamentally change our understanding of space, time, and information in the universe. Applied to cosmology, the holographic principle suggests that our three-dimensional universe might be encoded on a two-dimensional surface at its boundary. This radical idea challenges our intuitive understanding of reality and suggests that the universe's true nature might be very different from what we directly observe. The study of black holes has revealed deep connections between gravity, quantum mechanics, and information theory that may be relevant to understanding cosmic scale. The information paradox, the question of what happens to information that falls into a black hole, touches on fundamental questions about the nature of space and time. Recent developments in black hole physics, including the discovery of Hawking radiation and the holographic principle, suggest that black holes are not the simple objects described by classical general relativity. Instead, they appear to be complex quantum systems that challenge our understanding of causality and information flow. The Event Horizon Telescope's images of supermassive black holes in M87 and our own galaxy have provided the first direct visual evidence of these extreme objects. These observations confirm many predictions of general relativity, while opening new questions about black hole physics and the nature of space-time near event horizons. The study of primordial black holes, hypothetical black holes that could have formed in the early universe, connects black hole physics to cosmology and the search for dark matter. If primordial black holes exist, they could make up some fraction of the universe's dark matter and provide windows into the extreme physics of the early cosmos. The cosmic neutrino background represents another relic from the early universe that carries information about cosmic scale and evolution. These ghostly particles, produced when the universe was just 1 second old, fill all of space with a density of roughly 330 particles per cubic centimeter. Despite their abundance, cosmic neutrinos are incredibly difficult to detect because they interact so weakly with matter. No experiment has yet directly detected the cosmic neutrino background, though its existence is strongly supported by theoretical calculations and indirect observations. Future neutrino detectors may eventually observe these primordial particles, providing new insights into the universe's first second and the physics of the early cosmos. The properties of cosmic neutrinos could also help resolve questions about neutrino masses and their role in cosmic structure formation. The cosmic web's evolution over time reveals how the universe has grown from nearly uniform conditions to the complex structure we observe today. Computer simulations like the Millennium Simulation and the Illustris project have modeled this evolution in unprecedented detail, tracking billions of particles over cosmic time. These simulations show how tiny density fluctuations in the early universe grew through gravitational attraction to form the first stars and galaxies. The feedback from stellar explosions and black hole activity then shaped subsequent galaxy formation, creating the diverse population of galaxies we observe today. The comparison between simulations and observations has revealed both successes and challenges in our understanding of galaxy formation. While simulations successfully reproduce the large-scale structure of the universe, they struggle to explain some details of galaxy properties, suggesting that our models may be incomplete. The role of baryonic physics, the behavior of ordinary matter in stars, gas, and black holes, adds complexity to cosmic structure formation that is difficult to model accurately. The feedback from supernovae, stellar winds, and active galactic nuclei can dramatically affect how galaxies form and evolve over cosmic time. Recent advances in computational power and numerical techniques have enabled more realistic simulations that include detailed models of star formation, black hole growth, and galactic feedback processes. These next-generation simulations are beginning to reproduce observed galaxy properties with unprecedented accuracy. The study of galaxy evolution across cosmic time has revealed how the universe's star formation rate has changed dramatically over its history. The cosmic star formation rate peaked when the universe was about 3 billion years old and has been declining ever since, suggesting that the universe's most active period of star formation is in the past. This decline in star formation is partly due to the consumption of gas reservoirs that fuel star formation, and partly due to feedback processes that heat and expel gas from galaxies. The accelerating expansion of the universe also plays a role by making it increasingly difficult for galaxies to accrete new gas from their surroundings. The future evolution of cosmic structure will be dominated by dark energy's accelerating expansion. As space expands faster and faster, it will become increasingly difficult for gravity to pull matter together into new structures. Eventually, even bound systems like galaxy clusters may be torn apart by the expansion of space. In the far future, perhaps 100 trillion years from now, star formation will cease as galaxies exhaust their gas supplies and can no longer accrete new material. The universe will enter a degenerate era dominated by slowly cooling white dwarf stars, neutron stars, and black holes. Even further in the future, proton decay may cause all ordinary matter to disintegrate, leaving only black holes as the dominant form of mass in the universe. These black holes will slowly evaporate through Hawking radiation over timescales that dwarf the current age of the universe by countless orders of magnitude. The ultimate fate of the universe depends on the nature of dark energy and whether it remains constant or evolves over time. If dark energy continues to accelerate expansion, the universe may end in a big rip, where even atoms are torn apart by the expansion of space. Alternatively, if dark energy weakens over time, the universe might eventually recollapse in a big crunch that reverses the Big Bang. Other scenarios include cyclic universes that undergo repeated cycles of expansion and contraction, though current observations favor continued acceleration and expansion. The study of cosmic scale has profound implications for our understanding of humanity's place in the universe. We exist on a tiny planet orbiting an ordinary star in an unremarkable galaxy among trillions of others in an observable universe that may itself be just a small part of a much larger cosmos. Yet this cosmic perspective, rather than diminishing our significance, highlights the remarkable nature of our existence. The atoms in our bodies were forged in the nuclear furnaces of ancient stars, connecting us directly to the cosmic processes that have shaped the universe over billions of years. The elements that make up our bodies tell a story of cosmic evolution spanning billions of years. The hydrogen in our water was created in the Big Bang itself, while the carbon in our DNA was forged in the cores of massive stars that lived and died before our solar system even existed. The iron in our blood was created in supernova explosions that scattered heavy elements throughout the galaxy, enriching the gas clouds from which new stars and planets would eventually form. This cosmic recycling process means that we are literally made of stardust, as Carl Sagan famously observed. Every atom in your body, except for hydrogen, was created in the nuclear furnace of a star or in the violent explosion that marked its death. We are not separate from the universe. We are the universe becoming aware of itself. The Gaia hypothesis, proposed by James Lovelock, suggests that Earth functions as a single, self-regulating system. When viewed from the cosmic perspective, this idea extends to the entire universe, where galaxies, stars, and planets all participate in vast cycles of matter and energy that connect the smallest scales to the largest. The anthropic principle takes this connection even further, suggesting that the universe's fundamental constants appear fine-tuned for the existence of complexity and life. The strength of the electromagnetic force, the mass of the proton, and dozens of other parameters seem precisely calibrated to allow atoms to form, stars to shine, and planets to harbor life. If the strong nuclear force were just 5% weaker, deuterium wouldn't form and stars couldn't produce the heavy elements necessary for rocky planets and life. If it were 5% stronger, all hydrogen would have been converted to helium in the Big Bang, leaving no fuel for long-lived stars like our Sun. The fine-tuning of physical constants has sparked intense debate among scientists and philosophers. Some argue that it provides evidence for design or purpose in the universe, while others suggest that we exist in a multiverse where all possible values of constants are realized somewhere. And we naturally find ourselves in a region compatible with our existence. The weak anthropic principle simply states that we observe the universe to have properties compatible with our existence because we exist to observe it. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point in its history. These philosophical questions become even more profound when we consider the possibility of other forms of life in the universe. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy by considering factors like star formation rates, the fraction of stars with planets, and the likelihood of life developing. Recent discoveries of exoplanets have revolutionized our understanding of planetary systems and the potential for life beyond Earth. The Kepler Space Telescope discovered thousands of exoplanets, revealing that planetary systems are common throughout the galaxy and that Earth-sized planets exist in the habitable zones of many stars. The James Webb Space Telescope is now studying the atmospheres of these exoplanets, searching for biosignatures that might indicate the presence of life. Water vapor, oxygen, methane, and other molecules could provide evidence for biological processes on distant worlds, potentially answering one of humanity's most profound questions: are we alone? The search for extraterrestrial intelligence continues through projects like SETI, which monitors radio signals from space for signs of technological civilizations. The Breakthrough Listen project uses some of the world's most sensitive radio telescopes to search for artificial signals from nearby star systems. The Fermi paradox highlights the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for it. If the galaxy contains billions of potentially habitable planets and has existed for billions of years, where is everybody? This question has profound implications for our understanding of life's prevalence and the future of intelligence in the universe. Possible solutions to the Fermi paradox range from the idea that life is extremely rare to the possibility that advanced civilizations tend to destroy themselves or transcend the need for interstellar communication. The Great Filter hypothesis suggests that there may be evolutionary bottlenecks that prevent most life from reaching technological sophistication. The concept of a technological singularity, a point where artificial intelligence surpasses human intelligence and begins improving itself at an exponential rate, adds another dimension to questions about the future of intelligence in the universe. If such singularities are common, they might explain why we don't observe obvious signs of galactic civilizations. The study of astrobiology has expanded our understanding of life's potential by revealing extremophile organisms that thrive in conditions previously thought uninhabitable. From bacteria living in boiling hot springs to organisms surviving in the intense radiation around nuclear reactors, life on Earth has proven remarkably adaptable to hostile environments. These discoveries have expanded the concept of habitable zones around stars and the types of environments where life might exist on other worlds. Subsurface oceans on moons like Europa and Enceladus might harbor life, while the upper atmospheres of Venus or the methane lakes of Titan represent other potential habitats for exotic forms of life. The possibility of life existing in the clouds of Venus has gained renewed attention following the controversial detection of phosphine in the planet's atmosphere. While the interpretation of this observation remains debated, it highlights how our understanding of habitability continues to evolve as we learn more about extreme environments. The concept of panspermia suggests that life might spread between worlds through natural processes, potentially making life a galactic phenomenon rather than isolated planetary occurrences. Meteorite impacts can eject material from planetary surfaces at velocities sufficient to escape gravitational wells, potentially carrying microorganisms to other worlds. Studies of meteorites from Mars found on Earth have revealed that rocks can survive the journey between planets while preserving potential biosignatures. While no definitive evidence for Martian life has been found in these meteorites, they demonstrate that interplanetary transfer of life is at least theoretically possible. The search for life in our own solar system continues with missions to Mars, Europa, Enceladus, and other potentially habitable worlds. The Perseverance rover is collecting samples from Mars that will eventually be returned to Earth for detailed analysis, while future missions to the icy moons of Jupiter and Saturn will search for signs of life in their subsurface oceans. The discovery of life anywhere in our solar system would have profound implications for understanding life's prevalence throughout the universe. If life arose independently on multiple worlds in our solar system, it would suggest that life is common wherever conditions permit, dramatically increasing the likelihood of finding life around other stars. The study of cosmic evolution reveals that the universe has become increasingly complex over time, from simple hydrogen and helium in the early cosmos to the intricate structures of galaxies, stars, planets, and life. This increase in complexity appears to violate the second law of thermodynamics, which states that entropy should increase over time. However, the universe as a whole is not a closed system. It's expanding and cooling, allowing local decreases in entropy to occur as long as the total entropy continues to increase. The formation of stars, planets, and life represents local concentrations of order that are possible because the universe is far from thermal equilibrium. The arrow of time which distinguishes past from future emerges from this thermodynamic gradient. The universe began in a highly ordered state with low entropy and has been evolving toward higher entropy ever since. This process drives the formation of structure and the evolution of complexity throughout cosmic history. The concept of cosmic evolution extends beyond physics to include the evolution of information and complexity. The universe has evolved from simple initial conditions to systems capable of processing information, storing memories, and even contemplating their own existence. We represent the universe's attempt to understand itself. This perspective suggests that consciousness and intelligence may be fundamental features of cosmic evolution rather than mere accidents. The universe's ability to give rise to observers who can comprehend its vastness and beauty might be as significant as any of its physical properties. The participatory universe hypothesis proposed by physicist John Wheeler suggests that observation and measurement play fundamental roles in determining physical reality. In this view, conscious observers are not passive recipients of information about the universe, but active participants in its ongoing creation. Quantum mechanics supports this idea through phenomena like wave function collapse, where the act of measurement appears to determine which of many possible outcomes becomes real. While the interpretation of quantum mechanics remains controversial, it raises profound questions about the relationship between consciousness and physical reality. The many-worlds interpretation of quantum mechanics suggests that all possible outcomes of quantum measurements occur in parallel universes, with consciousness somehow selecting which branch of reality we experience. If true, this would mean that the universe is far larger and stranger than even our most ambitious cosmological models suggest. The implications of the many-worlds interpretation extend far beyond quantum mechanics to encompass the ultimate nature of reality itself. If every quantum event splits the universe into multiple branches, then there are countless versions of you reading this script in parallel universes, each experiencing slightly different outcomes of quantum measurements that have occurred throughout cosmic history. This quantum multiverse would dwarf even the cosmic multiverse proposed by eternal inflation theory. While the cosmic multiverse might contain different bubble universes with varying physical laws, the quantum multiverse would contain every possible history that quantum mechanics allows, creating an infinite branching tree of parallel realities. The measurement problem in quantum mechanics becomes even more profound when considered on cosmic scales. If the universe itself is a quantum system, as many physicists believe, then what causes the wave function of the entire cosmos to collapse? Some theories suggest that consciousness plays a fundamental role, while others propose that decoherence through environmental interactions provides the answer. The concept of quantum entanglement adds another layer of mystery to our understanding of cosmic scale. When particles become entangled, they remain connected regardless of the distance separating them, with measurements on one particle instantly affecting its partner, even across galactic distances. This spooky action at a distance, as Einstein called it, suggests that the universe is more interconnected than classical physics would predict. Recent experiments have demonstrated quantum entanglement between particles separated by hundreds of kilometers, and theoretical work suggests that entanglement might exist on cosmic scales. Some physicists propose that the entire universe emerged from a quantum-entangled state during inflation, creating correlations that persist across the observable cosmos. The holographic principle, emerging from black hole physics and string theory, provides another perspective on cosmic scale that challenges our intuitive understanding of space and dimension. This principle suggests that all the information contained in a volume of space can be encoded on its two-dimensional boundary, much like a hologram encodes three-dimensional images on a flat surface. Applied to cosmology, the holographic principle implies that our three-dimensional universe might be a projection from information encoded on a distant two-dimensional surface. This radical idea suggests that space itself might be emergent rather than fundamental, arising from more basic information theoretic processes. String theory, our most ambitious attempt to unify quantum mechanics and general relativity, proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings existing in multiple dimensions beyond the three spatial dimensions we experience. These extra dimensions might be compactified at scales so small that we cannot detect them directly. The landscape of string theory contains an estimated 10 to the 500th possible vacuum states, each corresponding to a different way the extra dimensions could be configured. Each vacuum state would have different physical laws and constants, potentially explaining the apparent fine-tuning of our universe as an environmental selection effect in a vast landscape of possibilities. The concept of brain cosmology derived from string theory suggests that our universe might be a three-dimensional membrane floating in higher dimensional space. Other brains might exist parallel to ours, occasionally colliding and creating new Big Bang events. These brain collisions could explain the origin of our universe and predict the existence of parallel cosmos beyond our observation. The study of cosmic inflation has revealed that our observable universe might be just one patch in a much larger inflating space. Eternal inflation theory suggests that inflation never completely ends, but continues in some regions while ending in others, creating an infinite number of bubble universes with potentially different physical properties. Each bubble universe in the eternal inflation scenario would have its own Big Bang event, its own cosmic history, and potentially its own physical laws. The bubbles would be causally disconnected from each other, making direct observation impossible, but raising profound questions about the nature of physical law and cosmic uniqueness. The anthropic landscape combines eternal inflation with string theory to suggest that we live in a multiverse where all possible combinations of physical laws and constants are realized somewhere. In this view, the apparent fine-tuning of our universe for life is simply a selection effect. We exist in a region of the multiverse compatible with our existence because we couldn't exist anywhere else. Critics of anthropic reasoning argue that it abandons the search for deeper explanations in favor of environmental selection effects. They contend that apparent fine-tuning might have fundamental physical explanations that we haven't yet discovered, rather than being the result of cosmic lottery in a multiverse. The debate over the multiverse and anthropic reasoning touches on fundamental questions about the nature of scientific explanation and the limits of empirical knowledge. If other universes are forever beyond our observation, can theories about them be considered scientific? How do we test ideas about regions of reality that are fundamentally unobservable? These questions push the boundaries between science and philosophy, challenging us to think carefully about what we can know and how we can know it. The scientific method relies on observation and experimentation, but multiverse theories deal with phenomena that might be forever beyond empirical verification. Despite these challenges, multiverse concepts continue to emerge from our best theories of fundamental physics and cosmology. The mathematical consistency and explanatory power of these ideas suggest that they might represent genuine insights into the nature of reality, even if direct confirmation remains impossible. The cosmic perspective reveals that our understanding of scale extends far beyond mere size to encompass the fundamental nature of space, time, matter, and information. The universe appears to be not just vast in extent but infinite in depth, with layers of reality that we are only beginning to explore. The emergence of complexity from simple, initial conditions represents one of the most remarkable features of cosmic evolution. The universe began with nearly uniform distributions of matter and energy, but has evolved to produce galaxies, stars, planets, life, and consciousness through the action of physical laws operating over cosmic time. This emergence of complexity appears to be a fundamental feature of cosmic evolution rather than a rare accident. Wherever we look in the universe, we see evidence for the spontaneous organization of matter into increasingly complex structures, from the formation of the first atoms to the evolution of life and intelligence. The principle of cosmic evolution suggests that the universe has an inherent tendency toward increasing complexity and organization, despite the second law of thermodynamics. This apparent contradiction is resolved by recognizing that the universe is not in thermal equilibrium, but is constantly driven away from equilibrium by expansion and cooling. The far future of the universe will be dominated by the continued acceleration of cosmic expansion driven by dark energy. As space expands faster and faster, it will become increasingly difficult for gravity to hold structures together, eventually leading to the dissolution of galaxy clusters, galaxies, and even solar systems. In the very far future, perhaps 10 to the 100 years from now, even protons might decay, causing all ordinary matter to disintegrate into elementary particles and radiation. The universe would then be dominated by black holes, which would slowly evaporate through Hawking radiation over timescales that dwarf the current age of the universe by countless orders of magnitude. The ultimate fate of the universe depends on the nature of dark energy and whether it remains constant or evolves over time. If dark energy continues to accelerate expansion, the universe might end in a big rip, where even atoms are torn apart by the expansion of space. Alternatively, if dark energy weakens, the universe might eventually recollapse in a big crunch. Other scenarios include cyclic universes that undergo repeated cycles of expansion and contraction, potentially creating an eternal sequence of Big Bangs and Big Crunches. Some theories suggest that our Big Bang might have been preceded by a previous universe that collapsed and rebounded, making our cosmos just one cycle in an infinite sequence. The study of cosmic microwave background polarization might eventually provide evidence for these cyclic scenarios by detecting gravitational wave signatures from previous cosmic cycles. Such observations would revolutionize our understanding of cosmic history and the ultimate nature of space and time. The concept of cosmic consciousness emerges from considering the universe's evolution toward increasing complexity and information processing capability. If this trend continues, the universe might eventually develop forms of consciousness and intelligence that transcend anything we can currently imagine. Some physicists and philosophers have speculated about the possibility of cosmic-scale intelligence emerging from the complex interactions of matter and energy throughout the universe. Such intelligence might operate on timescales and spatial scales that make human consciousness seem like a brief flicker in comparison. The idea that the universe might be evolving toward some form of cosmic consciousness connects to ancient philosophical and religious traditions that view consciousness as a fundamental feature of reality rather than an emergent property of complex matter. Modern physics provides new contexts for these ancient ideas through quantum mechanics and cosmology. The participatory universe concept suggests that consciousness and observation play fundamental roles in determining physical reality. In this view, the universe is not a collection of objects existing independently of observers, but a participatory system where consciousness and cosmos co-evolve together. The participatory universe concept gains support from quantum mechanics, where the act of measurement appears to play a fundamental role in determining which of many possible outcomes becomes real. If consciousness is required for wave function collapse, then observers are not passive recipients of information about the universe, but active participants in its ongoing creation and evolution. This idea extends to cosmology through the quantum origin of cosmic structure. The tiny fluctuations that grew into galaxies and galaxy clusters began as quantum uncertainties in the early universe. If consciousness plays a role in quantum measurement, then the large-scale structure of the cosmos might be intimately connected to the emergence of observers capable of contemplating their own existence. The fine-tuning of physical constants takes on new meaning in this context. Rather than being accidental or the result of selection effects in a multiverse, the apparent optimization of the universe for complexity and consciousness might reflect a deeper connection between mind and cosmos that we are only beginning to understand. The information-theoretic approach to physics suggests that information, rather than matter or energy, might be the most fundamental aspect of reality. In this view, particles, forces, and even space-time itself emerge from underlying information processing, making the universe more like a vast computation than a mechanical system. Digital physics takes this idea to its logical conclusion, proposing that the universe is literally a computer simulation running on some vast computational substrate. While this might sound like science fiction, serious physicists have explored the possibility that reality has a discrete, digital structure at the smallest scales. The holographic principle supports this information-theoretic view by suggesting that all the information in a volume of space can be encoded on its boundary. This implies that three-dimensional space might be emergent from more fundamental two-dimensional information processing, challenging our basic assumptions about the nature of spatial dimensions. Quantum error correction, a technique developed for quantum computing, has found unexpected applications in understanding black hole physics and the holographic principle. The mathematics of error correction might describe how information is preserved and processed in quantum gravity, providing new insights into the fundamental nature of space-time. The emergence of space-time from more basic information, theoretic processes, represents one of the most radical ideas in modern physics. If space and time are not fundamental but arise from quantum entanglement and information processing, then our entire understanding of cosmic scale and structure might need to be reconsidered. Loop quantum gravity provides an alternative approach to quantum gravity that suggests space-time has a discrete, granular structure at the Planck scale. In this theory, space is woven from quantum loops, and the smooth space-time of general relativity emerges as an approximation valid at larger scales. The implications of discrete space-time for cosmic scale are profound. If space and time are made of indivisible units, then there might be fundamental limits to how finely we can divide space and time, potentially affecting our understanding of infinity and continuity in physics. Causal set theory takes discreteness even further, proposing that space-time consists of discrete events connected by causal relationships. In this view, the continuous space-time of general relativity emerges from the statistical behavior of vast numbers of discrete causal connections, much like the smooth flow of water emerges from the motion of individual molecules. These approaches to quantum gravity suggest that our understanding of cosmic scale might be incomplete. The smooth, continuous space-time that we observe on large scales might be an emergent approximation of more fundamental discrete processes operating at the Planck scale. The study of black hole information paradox has revealed deep connections between gravity, quantum mechanics, and information theory that challenge our understanding of space and time. The paradox arises because general relativity suggests that information falling into a black hole is lost forever, while quantum mechanics demands that information be conserved. Recent developments in black hole physics, including the discovery of black hole complementarity and the holographic principle, suggest that information is not lost but is encoded in subtle correlations between the black hole and its environment. This resolution requires abandoning our classical notions of locality and causality in favor of more quantum mechanical descriptions. The firewall paradox represents another challenge to our understanding of black hole physics and spacetime. This paradox suggests that either general relativity, quantum mechanics, or our understanding of locality must be modified to resolve contradictions in black hole physics. These paradoxes in black hole physics might seem remote from questions of cosmic scale, but they touch on fundamental issues about the nature of space, time, and information that affect our understanding of the universe at all scales. The resolution of these paradoxes might require new physics that could revolutionize cosmology. The study of cosmic inflation has revealed that quantum fluctuations can be amplified to cosmic scales, creating the seeds for all structure in the universe. This process connects the smallest scales of quantum mechanics to the largest scales of cosmology in a direct and observable way. The cosmic microwave background preserves a snapshot of these quantum fluctuations from when the universe was just 380,000 years old. The statistical properties of temperature variations in this ancient light provide direct evidence for quantum processes operating during inflation. Future observations of gravitational waves from inflation could provide even more direct evidence for quantum gravity effects in the early universe. These primordial gravitational waves would carry information about physics at energy scales approaching the Planck scale, where quantum gravity effects become important. The cosmic neutrino background represents another relic from the early universe that connects particle physics to cosmology. These ghostly particles, produced when the universe was just 1 second old, carry information about the fundamental forces and particles that governed the early cosmos. The properties of neutrinos, their masses, mixing angles, and interaction strengths affect cosmic structure formation and the evolution of the universe. Precision measurements of cosmic structure can therefore provide insights into neutrino physics that complement laboratory experiments. The search for sterile neutrinos, hypothetical particles that interact even more weakly than ordinary neutrinos, represents one frontier where particle physics and cosmology intersect. These particles could make up some fraction of dark matter while affecting the formation of the first stars and galaxies. The cosmic ray spectrum extends to energies far beyond what we can achieve in particle accelerators, providing natural laboratories for studying fundamental physics. The most energetic cosmic rays carry more energy than entire atomic nuclei accelerated to nearly the speed of light. The sources of ultra-high energy cosmic rays remain mysterious, but they likely involve some of the most extreme objects in the universe, such as supermassive black holes, neutron star mergers, or exotic phenomena we haven't yet discovered. Understanding these sources requires connecting particle physics to astrophysics and cosmology. The GZK cutoff, predicted by the interaction of ultra-high energy cosmic rays with the cosmic microwave background, provides a natural test of fundamental physics on cosmic scales. Observations of cosmic rays at the highest energies can probe both particle physics and the structure of space-time itself. The study of cosmic magnetic fields reveals another aspect of cosmic scale that connects local physics to global structure. Magnetic fields thread through galaxies, galaxy clusters, and the cosmic web, affecting the behavior of charged particles and the formation of structure throughout the universe. The origin of cosmic magnetic fields remains one of the unsolved problems in astrophysics. These fields might have been generated during inflation created by the first stars and galaxies, or produced through other mechanisms we haven't yet identified. Understanding magnetic field evolution requires connecting plasma physics to cosmology. Primordial magnetic fields, if they exist, could have affected the formation of the first stars and the reionization of the universe. These fields might also have influenced the cosmic microwave background and the large-scale structure of the universe in ways that we are only beginning to explore. The study of cosmic voids has revealed that these seemingly empty regions are not completely devoid of matter, but contain a sparse network of dark matter filaments and gas. The properties of voids provide sensitive tests of dark energy and modified gravity theories. Void galaxies, the rare galaxies that exist within these empty regions, have unusual properties that reflect their isolated environments. These galaxies provide natural laboratories for studying galaxy formation and evolution in extreme environments with minimal external influences. The cosmic web's evolution over time reveals how the universe has grown from nearly uniform conditions to the complex structure we observe today. The filaments and nodes of this web continue to evolve as matter flows along dark matter highways and accumulates in massive galaxy clusters. Future surveys will map the cosmic web in unprecedented detail, revealing how dark matter, dark energy, and ordinary matter interact to create the largest structures in the universe. These observations will provide new tests of our cosmological models and potentially reveal new physics beyond the standard model. The concept of cosmic variance represents a fundamental limit to our knowledge of the universe's properties. Because we can observe only one realization of cosmic evolution, there are statistical uncertainties in our measurements that cannot be reduced, no matter how precise our instruments become. This cosmic variance affects our ability to measure cosmological parameters and test theories about the early universe. Understanding these limitations is crucial for interpreting observations and designing future experiments to probe the fundamental nature of the cosmos. The participatory universe concept gains support from quantum mechanics, where the act of measurement appears to play a fundamental role in determining which of many possible outcomes becomes real. If consciousness is required for wave function collapse, then observers are not passive recipients of information about the universe, but active participants in its ongoing creation and evolution. This idea extends to cosmology through the quantum origin of cosmic structure. The tiny fluctuations that grew into galaxies and galaxy clusters began as quantum uncertainties in the early universe. If consciousness plays a role in quantum measurement, then the large-scale structure of the cosmos might be intimately connected to the emergence of observers capable of contemplating their own existence. The fine-tuning of physical constants takes on new meaning in this context. Rather than being accidental or the result of selection effects in a multiverse, the apparent optimization of the universe for complexity and consciousness might reflect a deeper connection between mind and cosmos that we are only beginning to understand. The information-theoretic approach to physics suggests that information, rather than matter or energy, might be the most fundamental aspect of reality. In this view, particles, forces, and even space-time itself emerge from underlying information processing, making the universe more like a vast computation than a mechanical system. Digital physics takes this idea to its logical conclusion, proposing that the universe is literally a computer simulation running on some vast computational substrate. While this might sound like science fiction, serious physicists have explored the possibility that reality has a discrete, digital structure at the smallest scales. The holographic principle supports this information-theoretic view by suggesting that all the information in a volume of space can be encoded on its boundary. This implies that three-dimensional space might be emergent from more fundamental two-dimensional information processing, challenging our basic assumptions about the nature of spatial dimensions. Quantum error correction, a technique developed for quantum computing, has found unexpected applications in understanding black hole physics and the holographic principle. The mathematics of error correction might describe how information is preserved and processed in quantum gravity, providing new insights into the fundamental nature of space-time. The emergence of space-time from more basic information, theoretic processes, represents one of the most radical ideas in modern physics. If space and time are not fundamental but arise from quantum entanglement and information processing, then our entire understanding of cosmic scale and structure might need to be reconsidered. Loop quantum gravity provides an alternative approach to quantum gravity that suggests space-time has a discrete, granular structure at the Planck scale. In this theory, space is woven from quantum loops, and the smooth space-time of general relativity emerges as an approximation valid at larger scales. The implications of discrete space-time for cosmic scale are profound. If space and time are made of indivisible units, then there might be fundamental limits to how finely we can divide space and time, potentially affecting our understanding of infinity and continuity in physics. Causal set theory takes discreteness even further, proposing that space-time consists of discrete events connected by causal relationships. In this view, the continuous space-time of general relativity emerges from the statistical behavior of vast numbers of discrete causal connections, much like the smooth flow of water emerges from the motion of individual molecules. These approaches to quantum gravity suggest that our understanding of cosmic scale might be incomplete. The smooth, continuous space-time that we observe on large scales might be an emergent approximation of more fundamental discrete processes operating at the Planck scale. The study of black hole information paradox has revealed deep connections between gravity, quantum mechanics, and information theory that challenge our understanding of space and time. The paradox arises because general relativity suggests that information falling into a black hole is lost forever, while quantum mechanics demands that information be conserved. Recent developments in black hole physics, including the discovery of black hole complementarity and the holographic principle, suggest that information is not lost but is encoded in subtle correlations between the black hole and its environment. This resolution requires abandoning our classical notions of locality and causality in favor of more quantum mechanical descriptions. The firewall paradox represents another challenge to our understanding of black hole physics and space-time. This paradox suggests that either general relativity, quantum mechanics, or our understanding of locality must be modified to resolve contradictions in black hole physics. These paradoxes in black hole physics might seem remote from questions of cosmic scale, but they touch on fundamental issues about the nature of space, time, and information that affect our understanding of the universe at all scales. The resolution of these paradoxes might require new physics that could revolutionize cosmology. The study of cosmic inflation has revealed that quantum fluctuations can be amplified to cosmic scales, creating the seeds for all structure in the universe. This process connects the smallest scales of quantum mechanics to the largest scales of cosmology in a direct and observable way. The cosmic microwave background preserves a snapshot of these quantum fluctuations from when the universe was just 380,000 years old. The statistical properties of temperature variations in this ancient light provide direct evidence for quantum processes operating during inflation. Future observations of gravitational waves from inflation could provide even more direct evidence for quantum gravity effects in the early universe. These primordial gravitational waves would carry information about physics at energy scales approaching the Planck scale, where quantum gravity effects become important. The cosmic neutrino background represents another relic from the early universe that connects particle physics to cosmology. These ghostly particles, produced when the universe was just 1 second old, carry information about the fundamental forces and particles that governed the early cosmos. The properties of neutrinos, their masses, mixing angles, and interaction strengths affect cosmic structure formation and the evolution of the universe. Precision measurements of cosmic structure can therefore provide insights into neutrino physics that complement laboratory experiments. The search for sterile neutrinos, hypothetical particles that interact even more weakly than ordinary neutrinos, represents one frontier where particle physics and cosmology intersect. These particles could make up some fraction of dark matter while affecting the formation of the first stars and galaxies. The cosmic ray spectrum extends to energies far beyond what we can achieve in particle accelerators, providing natural laboratories for studying fundamental physics. The most energetic cosmic rays carry more energy than entire atomic nuclei accelerated to nearly the speed of light. The sources of ultra-high energy cosmic rays remain mysterious, but they likely involve some of the most extreme objects in the universe, such as supermassive black holes, neutron star mergers, or exotic phenomena we haven't yet discovered. Understanding these sources requires connecting particle physics to astrophysics and cosmology. The GZK cutoff, predicted by the interaction of ultra-high energy cosmic rays with the cosmic microwave background, provides a natural test of fundamental physics on cosmic scales. Observations of cosmic rays at the highest energies can probe both particle physics and the structure of space-time itself. The study of cosmic magnetic fields reveals another aspect of cosmic scale that connects local physics to global structure. Magnetic fields thread through galaxies, galaxy clusters, and the cosmic web, affecting the behavior of charged particles and the formation of structure throughout the universe. The origin of cosmic magnetic fields remains one of the unsolved problems in astrophysics. These fields might have been generated during inflation, created by the first stars and galaxies, or produced through other mechanisms we haven't yet identified. Understanding magnetic field evolution requires connecting plasma physics to cosmology. Primordial magnetic fields, if they exist, could have affected the formation of the first stars and the reionization of the universe. These fields might also have influenced the cosmic microwave background and the large-scale structure of the universe in ways that we are only beginning to explore. The study of cosmic voids has revealed that these seemingly empty regions are not completely devoid of matter, but contain a sparse network of dark matter filaments and gas. The properties of voids provide sensitive tests of dark energy and modified gravity theories. Void galaxies, the rare galaxies that exist within these empty regions, have unusual properties that reflect their isolated environments. These galaxies provide natural laboratories for studying galaxy formation and evolution in extreme environments with minimal external influences. The cosmic web's evolution over time reveals how the universe has grown from nearly uniform conditions to the complex structure we observe today. The filaments and nodes of this web continue to evolve as matter flows along dark matter highways and accumulates in massive galaxy clusters. Future surveys will map the cosmic web in unprecedented detail, revealing how dark matter, dark energy, and ordinary matter interact to create the largest structures in the universe. These observations will provide new tests of our cosmological models and potentially reveal new physics beyond the standard model. The concept of cosmic variance represents a fundamental limit to our knowledge of the universe's properties. Because we can observe only one realization of cosmic evolution, there are statistical uncertainties in our measurements that cannot be reduced, no matter how precise our instruments become. This cosmic variance affects our ability to measure cosmological parameters and test theories about the early universe. Understanding these limitations is crucial for interpreting observations and designing future experiments to probe the fundamental nature of the cosmos. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. How small are we inside the Milky Way? Discover how our solar system is just a tiny speck in the Orion arm, how the Gaia mission and Hubble Space Telescope have mapped our galactic neighborhood, why dark matter shapes the conditions for life, and much more. See you there.